Dear listeners, welcome to another video that covers the field of chemical calculations. This one's topic will be the composition of mixtures. My name is Pavlina Marvanova, and together we will look at some new quantities and variables, how to use and calculate them. The first quantity I would like to introduce in this video is density. Density, sometimes called specific mass, is calculated as the ratio of mass and volume. The symbol for density is Greek letter ρ, and the SI unit is kilogram per cubic meter. In our calculations, we may more often use density in gram per cubic centimeter. Density is a property that can characterize all states, solid, liquid, and gas. In most cases, we will use it in connection with liquids. Speaking about density, water is a gold standard for us. It is given that 1 cubic centimeter of water weighs 1 gram. It follows that the density of water is 1 gram per cubic centimeter. Practically, knowing the density means that we know the mass of the specific volume of a substance and vice versa. If the substance has a higher density than water, then this substance is heavier than water. An example can be a 35% hydrochloric acid solution with a density of 1.18 grams per cubic centimeter. 1 cubic centimeter of such a solution weighs 1.18 grams. Conversely, if a substance has a lower density than water, then it is lighter than water. For example, 1 cubic centimeter of diethyl ether with a density of 0.714 grams per cubic centimeter weighs only 0.714 grams. Density is a quantity that characterizes the composition of a given substance and is dependent on the temperature. The practical impact of these facts is that we cannot assume that hydrochloric acid solution, for example, will have the same density in all its concentrations. We can see from the table that a 10% solution has a different density than the 25% solution and a different density than the 35% solution. So, whenever we use density in our calculations, we can only relate the specific value to the solution whose concentration corresponds it to. The mass fraction, another important quantity, expresses the ratio of the mass of a component of the substance and the mass of the whole substance. The formula is the same, no matter if it is for a component within a mixture of substances or pure substance in a solution, or, for example, a specific atom within the whole molecule. The symbol for the mass fraction is W, and it has no unit. Why? Because we divide the mass by the mass. The value is always in the range from 0 to 1. Why? Because we divide the mass of the part, that is lower number, with the mass of the whole, that is always the higher number. We often convert the mass fraction to a mass percentage. It means that we multiply the calculated value of the mass fraction by 100 to obtain the corresponding mass percentage. The mass fraction 1 corresponds to 100%, and the mass fraction 0 corresponds to 0%. Analogically to the mass fraction, we have two more fractions, volume and molar fractions. We use them much less, but we will list them here for the completeness. The volume fraction phi is the ratio of the volume of the component and the volume of the whole. Again, this value has no unit, and again, the value is within the range of 0 to 1. By multiplying by 100, it can be converted again to the so-called volume percentage. The molar fraction X is then obtained as the ratio of the amount of substance of the component and the sum of the amounts of substance of all the components. Here, a sum of the molar fractions has to be 1, and again, it has no unit. So let's look at the first problem. What is the mass fraction of sodium chloride in a solution that was created by solving 5 grams of sodium chloride in 25 grams of the solution? Our unknown is the mass fraction W. And we have said that we calculate the mass fraction as a quotient of mass of the component, that means sodium chloride in this case, divided by the mass of the whole solution, sodium chloride and water in this case. Both values are given in the task. We have 5 grams of sodium chloride and in total 25 grams of the solution. So we will simply add it to the formula and calculate. The mass fraction is therefore 0.2. If we want to have the answer in percentage, we will multiply the mass fraction by 100, so we will get the value of 20%. Just an information to add, the mass percentage is sometimes also called the mass concentration in percentage. Therefore, if you come across this formulation in the task, it means that you have to calculate the mass fraction and then convert it to a percentage. Let's look at another problem. What mass of water needs to be added to 25 grams of potassium chloride to get a solution with the mass fraction of potassium chloride equal to 0.05? We know that the mass fraction is the ratio of the mass of a component divided by the mass of the whole. We have already said that. But our actual unknown is none of it. It is important to realize that the mass of the whole is actually the sum of the masses of all the components in the system. Thus, in this particular case, the mass of the whole consists of the mass of potassium chloride and the mass of water in which it is dissolved. Therefore, I can either stay with the original formula, that means to calculate the partial unknown mass of the whole and then the mass of the water. So it will be two steps procedure. Or I can use the modified formula where I express the unknown directly and calculate it in one step. I have decided for the first possibility, that is, I will first calculate the mass of the whole solution expressed from the formula, so we can see that the mass of the solution is calculated as a mass of potassium chloride divided by the mass fraction of potassium chloride. After the numerical substitution, when we have 25 divided by 0.05, we will get the answer that the mass of the solution in this case is 50 grams. As I have said, it is just a partial result. I know that the mass of the water, the unknown, which I am actually questioned for, is the mass of the whole solution, from which I'll subtract the mass of potassium chloride that is dissolved in it. The result is 475 grams of water then. Please note that for the calculation, we usually use the mass fraction in the form of a number from 0 to 1. This means that if the task gives us only the mass percentage, then we must convert it to the mass fraction by dividing it by 100. On this slide, I have prepared consideration of a mass fraction, which is a little different, but we will encounter it in a number of other more complex calculations, so we need to understand it correctly. The question is, how much of hydrochloric acid contains 150 grams of its 35% solution. This is quite important for us because hydrochloric acid as a 35% solution is actually a concentrated solution of this acid, and it is the one we use in practice in the laboratories. So for any experiment, this solution is actually our starting point. Being 35% practically means that it doesn't matter how much I take of this solution, but only 35% of this amount will always be the pure hydrochloric acid, which may then take part in some chemical reaction, for example, with sodium hydroxide or so. And the rest, the 65%, is the water. So back to the task. I know that I have 150 grams of a 35% solution of hydrochloric acid, and I want to find out how much of pure hydrochloric acid I really have. Pure acid means hypothetical 100% solution. As we said, when I use it in the experiment, I need to know what amount of the solution will take part in the possible chemical reaction. We already know this formula, and our unknown in this case is the mass of the pure substance of the hydrochloric acid in the given amount of its solution. The mass of the pure substance in this form is always calculated as the mass of the whole solution multiplied by the mass fraction. After the numerical substitution, we will get the answer. It's 52.5 grams. This is the mass of the pure hydrochloric acid in 150 grams of its 35% solution. Let me give you one advice. Here is the good point to check if you calculate correctly. Why? I would like to emphasize that the mass of the pure substance in the solution is always lower number than the mass of the whole solution. Why? Because the solution means the pure substance plus the water. This is the step where many unnecessary mistakes are done. So be always careful and think if your results are real. The composition of mixtures in terms of the proportion of the solute in the total volume of the solution is expressed by quantities called concentrations. If the amount of substance of a solute is dissolved in a given volume of the solution, then it is a molar or substance concentration, which we denote by a small letter c, and the unit is mole per cubic decimeter. This concentration is sometimes called molarity, and we can also meet it in this form. The unit is replaced by a large letter m. Thus, 2m means actually a 2-molar solution. That means a solution with a molar concentration of 2 moles per cubic decimeter. Let's make a short insertion here. We have already speak about the amount of substance in the previous video, and we know that it is the ratio of mass of the compound and its molar mass. Now, let's take a brief look at the derivation of one formula, which can be helpful for us in some calculations. We already know several ways how to calculate the amount of the substance. The most used are these two, using mass and molar mass, and molar concentration and volume. We can therefore derive a formula for calculation mass directly from the molar concentration in this form. The mass equals to the molar mass multiplies the molar concentration multiplies the volume. That allows us to skip one step in the calculations to make it shorter. If we don't consider the amount of the substance in the specific volume, but the mass of the pure substance in that volume, then we speak about the mass concentration. The unit is gram per cubic decimeter, and it is denoted as Greek letter rho with subscript of A. Please be careful not to confuse it with the density. The difference is in the mass. Whether we use the mass of the pure substance, then it is mass concentration of that substance, or whether we use the mass of the whole solution, then it is the density. Here we have the problem to solve. How many grams of sodium hydroxide do we need to prepare 25 milliliters of a 2 molar solution? The molecular relative mass of sodium hydroxide is given. Our unknown is the mass of sodium hydroxide. We calculate the mass commonly using the amount of the substance and the molar mass. We know that the molar mass is numerically equal to the molecular relative mass that is given in the task. But we don't know the amount of the substance. As we look at the task, we see there another variables, the molar concentration and volume. And we know that we can use them both to calculate the amount of the substance in a different way. Thus, a 2 molar solution means that the molar concentration is 2 moles per cubic decimeter. If we want to use the volume, then don't forget, it must be in the same units as the concentration, so it means in cubic decimeters. 25 milliliters corresponds to 0.025 cubic decimeter. We therefore calculate that the amount of the substance is 0.05 moles. Using this value in the original formula, we obtain the final value of 2 grams of sodium hydroxide. In this case, we could also use the derived formula for calculating mass directly from the molar concentration that we have derived on a previous slide. The procedure then would be one step shorter. Another problem. There is a question about the molar concentration of a 20% sulfuric acid solution. We have the information on the molecular relative mass of sulfuric acid, the density of a sulfuric acid, and also about the volume that is 1 liter. Our unknown, which we are supposed to calculate, is the molar concentration C. We can proceed in the calculation in different ways. The first is to gradually modify the formula to get it to the form where we know all values and can substitute them to the formula and calculate. So I know that I can calculate the molar concentration with the help of the mass, molar mass, and volume. The values of volume and molar mass we know. The mass is unknown for us. But we have an information about the mass percentage. This means mass fraction of the sulfuric acid in its solution. That and the left information in the task can lead me to the formula for calculating the mass using mass fraction and the mass of the whole solution. So I will substitute the mass of the sulfuric acid with the mass of the whole solution multiply mass fraction. And the mass of the whole solution, which is also unknown, can be calculated by using the volume and the density. So at the end, the formula for calculation, the molar concentration will look like this. I know all the variables that I have in the formula that are given in the task, so I can substitute all the letters with the numbers. And here, be careful while substituting the values into the formula, especially the value for the volume. Why? Because if we use the value of the density that is given in grams per cubic centimeter, we have to use also the volume in the suitable units. It means cubic centimeters. That's why in the dividend we put a number 1000, but in the divisor, because it was derived from the formula for molar concentration, and the molar concentration is in the mole per cubic decimeter. So in the divisor, the volume is given as 1 cubic decimeter. After the numerical calculation, I got the value of molar concentration 2.32 mole per cubic decimeter. Another way how to proceed is simply to calculate step by step. It means that the molar concentration is calculated with the help of amount of substance and the volume. The amount of substance is an unknown for me. I can calculate it with the help of the mass and the molar mass. I know the molar mass from the task, but the mass is unknown for me. I can calculate the mass with the help of the mass of the whole solution and the mass fraction. Once again, mass fraction is known, but the mass of the whole solution is unknown. I can calculate it with the help of density and the volume. And here I have both values, so it's no problem to calculate the value for the mass of the whole solution and then substitute it in the previous step to calculate the mass of the substance, then return to the previous step, calculate the amount of the substance, and substitute it in the first formula, and to count the molar concentration. Here we have it in numbers. The mass of the whole solution is 1140 grams. The mass of the pure substance of the sulfuric acid is then 228 grams. The amount of the substance is 2.32 moles, and the molar concentration is 2.32 mole per cubic decimeter. In the last part of this video, we will introduce a special type of calculation. In Czech, we call it a mixing equation, so I will call it this way also in this video. Imagine the situation. We work with a solution of specific substance in different concentrations. The mixing equations can exist in different forms. It depends on what information we have available. The most common forms are the following. One is based on the mass and mass fractions. The second on the amount of substance, or actually on the molar concentration and volume. Instead of mass fraction, it is also possible to use a volume fraction or volume percentage. The most common is this form. That's why we will use it for the calculation. This procedure is actually based on the principle of mass conservation. This means that I have one solution in which I have dissolved a certain mass of the substance, and I add to it the second solution in which I have dissolved another mass of the substance. Then the final solution must contain a mass of the substance which corresponds to the sum of the masses of that two parts. Since the mass of the pure compound can also be written as the mass of the whole solution multiplied by the mass fraction, and since we usually know, or it is easier to determine, the mass of the whole solution rather than just the mass of the dissolved component, the equation is most often used in the form you can see in the blue. The following rules are important for using this procedure. For a pure solvent, the mass fraction is always 0. Why? Because the mass fraction gives us the proportion of the substance in the whole solution, and if it is the pure solvent, it doesn't contain any of the substance. On the contrary, the pure substance has a mass fraction of 1, because in its entire volume there is only the given substance, nothing else. In the following slides, we will look at the specific examples where this can be used. But this is important. It can never be used in the system where a chemical reaction takes place. It is only for different solutions of the same substance. The procedure for calculations from chemical equations, it means where some chemical reaction takes place, will be the topic of another video. Let's look at the examples. The first is the solution. When we add one part of a pure substance having a mass fraction of 1 to 4 parts of a solvent with the mass fraction of 0, we obtain a final solution which is composed of 5 parts. Only one is the pure substance. The mass fraction of the substance in this solution will be 1/5. Another example is the concentration. We have a solution of the substance. In our case, it consists of 4 parts, one of which is the substance. The remaining 3 parts represent the solvent. So the mass fraction of the substance in this solution is 1/4. We add another amount of the pure substance with mass fraction 1. As a result, we obtain a final solution which consists of 5 parts, of which 2 parts are the substance and 3 parts the solvent. The mass fraction of the substance in the final solution will be 2/5. An opposite of concentration is the dilution. We have the original solution in which one part is the pure substance and 2 parts are the solvents. So the mass fraction is 1/3, and by adding 2 parts of the pure solvent with a mass fraction of 0, we again obtain a solution of 5 parts, of which only one is the pure substance and the remaining 4 are the solvent. The mass fraction of the substance in this final solution will be 1/5. And the last example is mixing, adding 2 solutions together. In the first solution, we have 2 parts of the solvent and 1 part of the substance. Mass fraction is 1/3. In the second solution, we have 2 parts. One is the substance and one is the solvent. So the mass fraction is 1/2. As a result, we get a solution of 5 parts again, which consists of 2 parts of the substance and 3 of solvent. The mass fraction of the substance in such a solution will be 2/5. We have here a problem to solve. What will be the final concentration of the potassium hydroxide solution formed by mixing 100 grams of a 10% solution, 250 grams of a 20% solution, and 150 grams of a 30% solution? So, at first, let's create an equation. We have 3 partial solutions, which we mix together, and they will create the final solution. As we have said, the mass of potassium hydroxide, which will be in the resulting solution, must be equal to the sum of the masses of potassium hydroxide, which is in the first solution, second solution, and the third solution. Our unknown in this case is the final concentration in percent. That means the mass fraction of the potassium hydroxide in the final solution, which is marked in blue. And now we add the numbers. The mass of the first solution is 100 grams, and the mass fraction of potassium hydroxide is 0.1. The mass of the second solution is 250 grams, and the mass fraction of the hydroxide is 0.2. The mass of the third solution is 150 grams, and the mass fraction of hydroxide is 0.3. The mass of the final solution is the sum of the masses of individual solutions. It means 500 grams. After calculation, we will get the equation in this form. 105 equals 500 multiplies the unknown. And the answer is that the mass fraction of potassium hydroxide in the final solution is 0.21. Transformed to the percentage, it is 21%. Another type of chemical problems where this type of procedure can be advantageously used is, for example, this. How much water is needed to prepare a saturated solution from 8 grams of boric acid? The mass fraction of boric acid in its saturated solution is 0.048. Let's explain here what the term saturated solution means. A saturated solution is a solution where, under given conditions, it means specific temperature and pressure, the maximal possible amount of the substance is dissolved in a specific amount of solvent. This quantity is usually called solubility, and the values can be found in chemical tables. The mass fraction that we need for the calculation is based on the solubility of boric acid under the given conditions in water. In our case, it is given in the task, so it's easier for us. So let's start solving. We have a solid boric acid, which we dissolve in some amount of water, and then we get a final solution. So the equation will look like that. We know that the mass of the final solution, again, can be calculated as the sum of the masses of the boric acid and the added water. At this moment, we have only one unknown in our equation. It is M2, so it means the mass of the water. From the task, we know that we have 8 grams of boric acid, and because it's solid, it means that it has mass fraction of 1. The mass of the water is unknown for us, and because it is a pure solvent, its mass fraction is 0. On the other side of the equation, we have the sum of the masses. One we know, it is 8 grams of boric acid, and the second is unknown. The mass fraction of boric acid is given in the task. When we calculate, we will get the equation in this form. You can see that on the left side of the equation, the unknown actually disappeared, so the equation once again becomes more simple. After calculation, in 2 steps, we will get to the answer that the mass of the water is 158.75 grams. So this value is the mass of water necessary to prepare a saturated solution from 8 grams of boric acid under these specific conditions. Before we get to the end, I would like to say one important thing. Commonly, there is more than just one way how to solve the chemical problems. For example, these two that we solve with the help of this so-called mixing equation can be solved, for example, by considering. It doesn't matter which procedure we choose. The important is to do it correctly and to get the correct result. To sum up, in this video, we have discussed the basic chemical calculation concerning the composition of mixtures. We have talked about quantities such as density, mass fraction, concentration, whether molar or mass, and we also introduced the procedure so-called mixing equation. Thank you very much for your attention, and we will see by the next video.